Oh, and I decided I actually want to keep iClicker for my purposes because I like how iClicker arranges your attendance, and then it's easy for me. So we're just going to do both. So you do need iClicker. But you do still have to do the Excel spreadsheet. So this is what we are doing right now. Good morning. Oh, I got something in the chat. Good morning, Sam. I'm glad you put something in the chat so that I know to put the chat. I needed that. Okay. And back there. This go. Yeah, we might do that. Yeah, we can do that. Sam, I'll send you an email when I get back to my office with a link. Oh, there it goes. Okay, don't forget that this Friday at 3 o'clock is Q&A with a chemist in 104. I keep moving it, it keeps coming back. But if you're in my lab, you'll be in lab. But we might not go the whole time, so you might be able to catch part of it. But so please check in on iClicker and on the seating chart, the Excel spreadsheet. I know it's double the pain, but it's going to be nice. Put that there. Oh, I got to put my chat back. Okay, there we go. Do you still use Reef? Yes, Victoria. Check in on Reef. Yes. I'm sorry, I didn't see your message in there. Yes, please check in on Reef. And then you two on Zoom, come down here and put your names in here. I am on Zoom. So everybody does both every time. Yay, thank y'all. Please make sure your name's accurate. Yes, ma'am. Yes. No, you can write on PowerPoint slides. Thank you very much. I really appreciate that. And when I reply this afternoon, once things settle down for me, I'll let you know how it goes from there. But thank you very much. I appreciate it. So please make sure that when you close the Excel spreadsheet, it's the sheets, it's not Excel, it's sheets. When you close sheets, if you come back to it, your stuff's still there, right? So that our seating chart is very accurate. So either you got to hit enter, you got to click a white cell, whatever it is. That's where we want to go. Okay, y'all ready? Everybody got attendance? Anybody issues with typing in their name? Pretty good? Okay, so I'm going to go ahead and close that. And I'm going to pull up this. This is kind of where we left off, right? Ooh, let's go this way. Right, remember this is what we wrote. I just typed it up real quick. But you should already have this in your notes, right? Okay, so before we start, and I want y'all to picture my 9-year-old doing this joke, not me, okay? All right? 9. Knock, knock. T-Rex. What? There's a dinosaur at your door and you want to know his name? He loves that joke. Like, I don't know how many times he has told me that joke. Like, it is one of his absolute favorites. It's crazy. So I figure I had to at least subject y'all to it once. Keep them coming. Does the quality keep going up or does the quality keep going down? It's a good mix. All right. Okay, so remember last time we were talking about how do we know if a reaction is going to be spontaneous or not, right? That was kind of our goal, name of the game. We need to know what's actually going to happen in the body spontaneously versus what's not going to go. So in order to be spontaneous, delta G must be negative, right? And we know we have a formula that relates the three factors really that control delta G, right? We have enthalpy, temperature, and entropy in our ghetto homies formula, right? And so for each parameter, like enthalpy, you could have delta H being negative or delta H being positive, right? If delta H is negative, it is exothermic. If it is positive, it is endothermic. And then you could talk about entropy, right? And entropy could be positive or entropy could be negative, right? That's where we got to at the end. But we also have to take into account temperature. But it's not a change in temperature, it's the actual temperature. So what is the temperature of most living systems? What are y'all? What is your temperature? What's your units on that? That is the F word. We don't use the F word in this class. I don't think I'm crazy, right? It's the F word. We don't use Fahrenheit. What do we use? Well, Kelvin's okay. Kelvin's okay. Celsius, about 37 Celsius. Yeah. Okay. Yeah. Yeah. Right. So a lot of times when you hear chemistry, when we talk about temperature, we talk about room temperature. So what's room temperature?
20.
Yeah, 21, 22, 25, something like that, right? That's depends on the room you're in. Right now it's feeling like 20. But right. So just be aware that there's a difference between room temperature and our actual temperature. And we love Celsius and Kelvin. No F words in here. No F words. Okay, so remember they had this little ooh, if I can, no. I'm not good at this. Okay. So remember we had that table, right? And I said, you don't have to memorize that table, right? So you don't have to memorize this either. I'm not asking you to memorize it. I'm just going to use this formula 4 times to illustrate a point. Okay, it's the same formula. And you're even given the formula, I believe, on your formula sheet. So it's not really any memorization, it's really understanding. Okay, so what happens when we talk about having a reaction that is exothermic with a very high delta S? I don't want to put in numbers. I just want to think about these equations in the abstract. So what would happen with delta G? How can I get a negative delta G in an exothermic reaction that has really high entropy? So what would happen to delta H? What's the charge on delta H? Delta H would be negative, right? Delta H would be negative. Tell me about delta S. What's delta S? Delta S is positive, right? Okay, so when we do this, what unit are we using for temperature? For this particular formula, we're not using the F word, right? So are we using Celsius or are we using Kelvin? We're going to use Kelvin. Why do we have to use Kelvin for this? There are no negative temperatures in Kelvin, right? There's absolute zero, and that's the coldest you can get. So you're never going to have a negative value for temperature. Temperature will always be positive. So in Kelvin, so never negative. Make sense? Okay, so if I have a negative, that's my delta H, minus a positive, right? And those are multiplied together. That's really negative and a negative, right? Okay, so what happens? If I have a negative and I'm going to add another negative number to it, what is delta G going to be? What? It's always going to be negative. So if you have an exothermic reaction with high entropy, delta G is always negative. So it's going to be what? Spontaneous. This one's going to be spontaneous. Always, always spontaneous, right? Okay. What if we have something that is still exothermic, but now we change our entropy, right? So what's going to happen to delta G? Delta H is still what? Negative. T is always going to be positive, right? So what's delta S? Delta S is going to be negative, right? Okay, so I have a negative, and then I'm going to add to that this negative, right? And then my T is positive, my S is negative. So what's a negative times a negative? We're going to get a positive, right? So we really have a negative and a positive. So tell me about spontaneity of this. Are I always going to be a negative delta G? When am I going to have a negative delta G? When my temperature is low. So when temperature is low, right, that positive number right here is going to be small, and my negative is going to overcome that. My negative delta H is going to overcome that. So when temperature is low, delta G is what? Negative. Right? Do you have to memorize anything? No, you have to know how to use the formula. Isn't that beautiful? I love when that happens. Okay. What if I have a reaction that is endothermic with high entropy? What's going to happen? Delta H is going to be positive. Okay. How about delta S? Positive. Okay. So if I have a positive and then I have this negative sign, right? I have this negative sign in front of this whole unit. So what's the prognosis? What's that? Well, they're not both positive. Yeah, when temperature is high, delta G is negative. So it's kind of the opposite. These two are kind of opposites of one another, right? Because what did we change? We just switched the signs. So if you understand the formula, cool. All right, endothermic with a low delta S. What is delta H? Positive. Okay. What is delta S? negative. Okay, so if I have a positive, and then I'm going to have a negative, I have a negative here, and then I have a negative delta S, what do I get? A positive. If I have a positive and a positive, am I ever going to have a negative delta G? So delta G is always positive. Do you see how these are opposites of one another? Okay. And y'all know y'all can log into the Zoom if you have your computer in front of you. If you want to have the screen like right in front of you, you can do that, even if you're not at home. Okay. So, right, we just determined there are 4 different conditions that can make a reaction spontaneous, right? It can be spontaneous all the time. So does it matter what your temperature is? No, it's going to be spontaneous. It can never be spontaneous. So it doesn't matter how hot it gets or how cold it gets, it's never going to happen. Or it can be spontaneous at high temperatures, or it can be spontaneous at low temperatures. And all you have to do is know your ghetto homies. And you're good. Right? Okay. I'm gonna be like, that is the only thing I learned this semester. No, you also learned great new jokes. Okay, so when we talk about spontaneity, right? The other important factor that we have to discuss is equilibrium. So Gibbs free energy is really, really closely related to our equilibrium constant, right? So when we see delta G, and what's that little circle at the top? That's standard conditions, right? And do we really care about standard conditions? No, what do we really care about? Standard biological conditions, which is when you add the prime to that, right? That's what we really want to know. We really want to know the prime. Okay, so we know that we can relate our Gibbs free energy to our equilibrium constant. So let's have a quick refresher of what equilibrium constant is. And don't forget that this R right here, right, there are 2 R's. There's the gas constant R, and then there's the energy R. Make sure that you use the right R in this equation, because you will have to use this equation in class and in homework and on the exam. It's the energy R. It's the gas constant R, not the energy R. Ooh, say it right. Okay. So let's have our quick refresher about what equilibrium constant means, right? So the equilibrium constant tells us about the reaction, right? Whether we're going to favor making products, or we're going to favor making reactants, or we're going to be at an equilibrium in the rates of the reaction. Are we at equilibrium in concentration? Like if I'm at equilibrium, if I have a reaction that's at equilibrium, does that mean that I have the same amount of reactants as products? Absolutely not. That equilibrium is in the rate of the reaction. So you have a equal rate of the forward reaction as you do a rate of the reverse reaction. So that's a good reminder from beginning chem. So if we have this reaction, right, we have our reactants here, we have our products here. If you're going to write the equilibrium expression, and you've done this, right? You've written equilibrium expressions. Yes. So what goes on the top? Our products concentration at equilibrium. Are all reactions at equilibrium inside the cell? Absolutely not. So I automatically know, okay, this is really how it chemically works, but we're going to have to talk about what happens when we're not at equilibrium. So we're going to talk about that. But to write an equilibrium expression, we put our products on the top, we put our reactants on the bottom, and you use superscripts to denote our coefficients, right? Good on that? So if we do this and we solve this equation and we get a value that is less than 1, that's telling us that we're going to favor the formation of reactants. If we have a K equilibrium that's greater than 1, we're going to favor the products. And if we're equal to 1, we're going to be at equilibrium, right? So this is pretty standard stuff. So really, the K at equilibrium tells us the directionality at standard conditions. That's awesome. That's great. None of our cells are at standard conditions. So we need to look at non-standard conditions. So when you were doing Chem 105, 106, right? And you were looking at equilibriums, what do we call it if you're not at equilibrium? It's not K anymore. It's what? Q. Q is the wannabe K. Y'all have heard that, right? We're not at equilibrium if we're going to talk about Q. So what I can do is I can say the actual free energy, this is our actual free energy, is equal to our free energy at standard conditions, right? Plus RT ln, not of K, but of Q, So if I wanted to represent Q, how do I represent Q? I do that same thing where I'm doing my products over my reactants, but instead of writing the little EQ, what do I write? I write a little I for the initial concentrations. Remember that? Yeah. Okay. So now let's take this situation and let's assume that we are at equilibrium. What happens when we're at equilibrium? Delta G is 0. What else? What about Q? What is Q? At equilibrium. Not 0. K. Right? Because that's the equilibrium constant. Q is equal to K. So if we plug that in, what happens? I get 0 plus RT ln of K, right? KEQ, we'll put EQ. So now what do? I can shuffle this over. These are my standard conditions, right? And I want to take, if I move the G over, right, that picks up a negative sign, but I don't want that to have a negative sign because that's what I'm solving for, right? So I just put my negative on this side. Make sense? Or you could say you just pulled around the other mess, whatever you want to think. Okay. So now let's talk about delta G in terms of direction of reactions, because now we can do that. So what happens if delta G is less than 0? Now we can relate this to equilibrium. We can relate this to directionality, right? So if delta G is less than 0, what do you know? Spontaneous. So now relate spontaneity to direction of a reaction. It goes to formation of products. So this favors what reaction? Forward, which is left to right. Make sense? So now give me the other condition. Delta G is greater than 0. This is going to favor reverse, right? This is right to left. So you're going to have some reactions inside of the cell that if you do the calculation, the pure math of the reaction, and you look at it and it's unfavorable, right? You look it up, you do the math, it's an unfavorable reaction. But sometimes inside the cell, it's actually favorable. Why? Why do you think, how is that possible? What did we just assume in this derivation of this equation? Equilibrium. We assumed equilibrium concentrations of all of our reactants and products. Is that what we find in the cell? No, absolutely not. So just because you look it up in the book and it gives you a delta G value, that isn't always right, because it really depends on the concentrations of the reactants and the products, right? Y'all know about Le Chatelier's principle, right? So these are shifts. So what happens if you increase the concentration of a reactant? What happens to the reaction? Shifts in the forward direction. What happens if you increase concentration of product? Shift in the reverse direction. We are going to apply that to biological systems this semester. So this is like, biochemistry is like the application of chemistry. I love it. Absolutely love it. Okay. All right. So we know that delta G is dependent upon delta H, our temperature, and delta S, right? So that's our equation. And up until now, we've talked about standard conditions, but I haven't specified exactly what they are. So here they are for your notes, that if you have that standard condition, you have that knot. It's talking about a constant pressure of 1 atm, which is pretty true for cells, right? Room temperature, ooh, we're not at room temperature, right? So this isn't really good for us, but chemistry-wise. And then the reactants and products are at 1 molar. That's not always true, right? Absolutely not. So a lot of times we use the biochemical standard conditions. The biochemical standard conditions are just like the standard conditions, but we're adding some other conditions to that. We have a pH of 7. We have a very high concentration of water, right? 55.5 molar. And then magnesium 2+, a lot of times is found in the cytosol and is required for all kinds of different reactions. And so typically that stays at 1 millimolar. But we're still, even if we solve for this, right, with all these conditions set, it's not an accurate representation of what actually happens inside the cell. So I want you to keep that in mind as you're doing all these calculations, that it's not really like that in a cell. Okay, so there are some reactions that are actually unfavorable, that will not go, period. They just won't go. So if you want that reaction to go in a biological system, how are you going to force that to happen? And it refers back to Le Chatelier's principle, right? If I have something like A plus B goes to C. Oh Lord. A plus B goes to C. And I'm going to tell you that this forward reaction is unfavorable. What do I do to force it in the forward direction? I could increase the concentration of reactants. What else could I do? That's true. I can decrease C. Okay, this is how biological systems work. If I decrease C, more of A and B is going to get converted to C, right? So how do I do that? I need another reaction. I need C plus D goes to E, right? What do we call C in this situation? An intermediate, chemistry-wise, an intermediate. So C is an intermediate. C is an intermediate. So when we have two reactions and they share an intermediate, we call that a coupled reaction. We call that a coupled reaction. So typically that first reaction is unfavorable. Your second reaction is favorable. And then when we're looking at combining two equations, what do we do to get the overall free energy of both reactions together? What do you do? Add them together. Add them together. And as long as the sum of the two is negative, they're both going to go, right? That's a coupled reaction. So a lot of times inside the cell, we use ATP hydrolysis as the coupled reaction, right? But do I gain energy by breaking a bond? Or I asked you this. No, I have to put energy in to break a bond. So in your book, you're going to see this image of ATP. This is ATP, right? And they highlight the bonds that are broken when we use ATP, right? So we get a negative value. Well, that doesn't make sense, right? It's not the cleavage of the bonds that provides energy. All bond breakage requires an input of energy, but it's what happens to those pieces after the hydrolysis that results in the energy, okay? So when I cleave, let's say I cleave right here, what am I going to end up with? What is this called now? It's not ATP anymore, it is adenosine diphosphate. And then as an abbreviation, what do we call this? PI, an inorganic phosphate group. We call it PI. So either one of these two things, so either the PI or the adenyl, can be actually hooked on to another molecule. And when you do that, so the bond's broken and one of these two things is attached to another molecule. When you do that, you have made a very, very highly reactive intermediate. And it's so crazy high, it's not going to stick around for very long, right? And that's where the energy comes from. So it's really that you're making a very highly reactive intermediate, and that's what drives the reaction. That's what gives you your negative delta G value, right? Okay. So let's talk about this coupled reaction, right? So let's do this. So if I have A plus B goes to C, then C plus D goes to E, right? That was my pretend reaction. I'm going to get delta G values for both. So the first one I'm going to say my delta G, not prime, and I'm going to call this 1 because this is reaction 1. I'm going to say it is +3 kilojoules per mole, right? Favorable or unfavorable? Unfavorable, absolutely unfavorable. But if I look at reaction 2 and I say my delta G naught 2 is something like -10. What do I do to get my overall reaction? Add them together. So I'm going to call this 3, right? And how did I get that? I just did delta G1 plus delta G2, and I get delta G3. I don't want to have the dot. Okay, so what do I get? -7. So now I can drive this top reaction. And we see this over and over and over again in biochemistry. Okay, so I want to share one other kind of cool thing. I think, did I put it on here? No, I don't think so. Let's see. No, I didn't, but I want to do it with y'all. Okay, so we use ATP for this a lot, right? We call it the energy currency of the cell. You got a question?
Yeah, for the ATP and PI example, would the ATP and PI be the intermediate?
No, the intermediate would be my X being hooked to the inorganic phosphate, or my X being hooked to ADP. And I'm going to show you that. I'll show you that in a reaction. So watch. Let's skip ahead and then I'll show you something cool, right? So here's an example of us using ATP to drive a reaction, right? So what we want to do is we want to take glutamate and we want to convert it to glutamine. So what's the difference between glutamate and glutamine? Look at the structures. Right here, instead of having an oxygen, what do I have? a nitrogen, but you should know your functional groups, right? You have to know your functional groups. Okay, so what happens in the conversion from glutamate to glutamine? It's unfavorable, right? It takes too much energy to do that. So how much energy is it costing us to go from glutamate to glutamine? How much energy? A positive 14. It's costing us energy. Our cells aren't going to do this normally, but we actually really need to in order to produce different amino acids, to get rid of nitrogen inside of our body, all that kind of stuff. So we have to figure out a way to make this favorable. So we couple this to ATP hydrolysis, right? So in the body, what actually ends up happening is that you have ATP hydrolyzed to ADP by glutamine synthetase. So what happens is this inorganic phosphate group, this is the PI, right, gets attached to glutamate in this very high energy intermediate. And then it doesn't stick around for very long, right? But the product gets used up. So now we can take this nitrogen, this is what we really wanted on our glutamate, we can take this nitrogen group and we can replace the inorganic phosphate with the nitrogen. So we can drive the reaction forward. So if we look at the other part of the equation, when we have ATP hydrolyzed to ADP, right? In the first part, we get ADP out. In the second part, what do we get out? Inorganic phosphate. Now what do we have? A delta G value of -30. So overall, these two coupled reactions will give us a negative delta G value. So now this reaction can be spontaneous. Yeah? Okay. All right, so we need ATP. We need a lot of ATP, right? So if you have the average person, so we'll say the average person is 100, let's say 70 kilograms, right? And 70 kilograms is like 154 pounds, right? It's an average person. What if I want to figure out how much ATP? You don't have to write this down. This is for fun. This is for fun. So if I want to know how much ATP does the average person use in a day, that's kind of an interesting thing, right? Okay, what do I need to know? How much the person weighs, right? What's their mass? What else do I need to know? No, that's just mass, just mass. What else? I need to know something about ATP. What do I need to know? I need to know two things about ATP. You're going to use about 100 moles of ATP per day. 100 moles of ATP per day. It's a lot, right? Okay. What else do I need to know if I want to do the math? I need to know the molecular weight of ATP. What's the molecular weight of ATP? I will give it to you. 507 grams per mole. Okay, now what do I do? If I have this information. Come on, y'all. Dimensional analysis, right? Stoichiometry, gotta love it. So I have 100 moles of ATP per day, right? Now what? And 1 mole of ATP. Oh my gosh, I feel like I'm in my 109 class and it's silence. So what do I get? Oh, if I could erase that. Anybody got a calculator? What do you get? What? 50,700? 50,700 grams. So what is that in kilograms? Move your decimal place 3 times. Come on, y'all.
2.7 kilograms.
Holy moly. What is that in pounds? 2.2, 110 pounds. I need 110 pounds of ATP a day. Do you eat that much stuff? How can you use 110 pounds of ATP in a day? Interconverting it back and forth. We're going to see this concept over and over and over again in biochemistry. The body is insanely good at recycling everything we use. Like your body is the ultimate recycling machine. There is no way that we could make this from scratch, right? 110 pounds, that's crazy. All right, I just thought that was interesting. Okay, so let's talk about ATP. So why ATP? Why is ATP the molecule that is going to be coupled and going to drive all these reactions? Why is ATP a unique molecule in that way, right? Why couldn't we use something else? Well, there are particular properties of ATP that make it perfect for releasing a phosphate group, right? So if you look at all those phosphates, what's the charge on an individual phosphate group? It's negative. It's negative, right? So if you have a couple of negative things strung together, is that really stable? No, it's really not, because of repulsion, right? Similar charges repel each other, right? So if we lose one phosphate group, that repulsion gets smaller, right? Okay. So the other thing that's nice is that once that inorganic phosphate group is released, now it can adopt different resonance forms with that double bond to one of the oxygens, right? And so it's not attached, covalently attached to anything. And so those bonds can move around. Whereas if you're stuck in the ATP molecule itself, you don't have as many resonance options, right? So that actually favors the release of those free phosphate ions, right? That's entropy, how much disorder you can have, right? And an ATP molecule is very ordered. All the bonds have to be in a particular place. In the released phosphate ion, it can move around, right? So that's entropy. And then the other thing, and we're going to come back to this concept kind of regular, is solvation, right? So when you put something into water, what happens? If it's also charged, what is the water going to do? It's going to cover whatever your substance is, right? Because if it's negative, the partial positive charges on the hydrogen are going to be attracted to the negative, right? So that's called solvation. So when you have these separate ion, you're going to have more solvation, which actually gives you a higher entropy, right? So remember, the universe is tending towards disorder, and so we want high entropy. And so those two things kind of have to do with entropy. Okay. So when we look at, oh, I did put it in there. I thought I did, but I put it in the wrong place. It's okay. So when we talk about the energy charge of the cell, right? We have three different forms of ATP. You can actually have ATP. You can hydrolyze one phosphate. What do you have? ADP, or you can hydrolyze two off and release a pyrophosphate, which is PPI, and get AMP, right? So you have a relationship between the concentration of those three forms at any given time in the cell, right? So under what conditions do I want to start building muscle, let's say? What are my concentrations going to have to be? What do I want more of? ATP, ADP, or AMP? ATP. So when we look at the ratio of those three things at any given time, we call that the energy charge, right? So when I'm ready to make things, my energy charge better be really what? High. But what happens when my energy charge gets low? You start feeling real hungry, right? Your energy charge gets low in the cell. Are you going to be making things? No. What are you going to start doing? Breaking them down. You're going to start breaking them down. So it gives you a readout on the cell. So when we do a calculation, you can actually calculate, there's a formula, I'll show it to you. that you can actually calculate the energy charge of the cell. And most cells stay between 0.7 and 0.9, which is where you have a lot of ATP. And that's really, really necessary for you to be able to do all the metabolism that you have to do inside the cell. So if your energy charge gets too low, you start going into starvation mode and you start breaking down your own body, right, in order to increase that energy charge. So here's our formula. You don't have to memorize it. You don't have to memorize it. Please don't try to memorize it. But here's our physiological range, right? What did we say? 0.7 to 0.9. So if you look in this range, what do we have the most of? Red is ATP, blue is ADP, and black is AMP. I have lots of ATP, right? At what point do I have equal concentrations of all three? At 0.5. So at 0.5, my concentration of ATP is equal to concentration ADP is equal to concentration of AMP, right? And so what we're going to do is we're going to look at what processes happen inside the cell depending on the energy charge. But energy charge is a readout. So a lot of times when we look at some of these biochemical pathways and we talk about their regulation, we're going to talk about energy charge. Like almost every time we talk about a regulation, we talk about energy charge. So if our energy charge is really low, that means we haven't eaten in a while. We want to convert energy-rich compounds like what? What are energy-rich compounds? Carbs can be, yeah, carbs. What else? Fats, right? This is the whole thing with a low-carb, low-fat diet. Then what does your body start doing? Breaking down your own fats inside the body, right? And we're going to convert them into energy depleted compounds, basically waste products, right? And then we're going to use that energy. So when we do that, when we undergo those catabolic pathways, we're going to make ATP, but at the same time, remember, was it Monday? When we talked about not only do you make ATP, but you are also shuffling electrons. Remember that? And we said we went from NAD plus to NADH. So NADH is an energy carrying molecule, and it's energy carrying because it's shuffling electrons, right? You also have something called NADPH, and we'll talk about why that one's different later. And then we talked about FAD converting to FADH2, right? And those are all really, really, really important in energy conversion reactions all across your cells, right? So all of these things that we just made, ATP and our reduced energy carrying molecules, are now going to be used for what? Right? Used for what? We have a low energy charge, so we are going to go grab our fats from the body. We're going to generate ATP. But why do we need to generate ATP? Why do we need to generate NADH? FADH2? For what? What's the point? To maintain all of our cellular functions, right? Because your cells are constantly needing proteins and all kinds of different molecules inside of the cell to function. So you're going to take that energy and you're going to use it to make things, right? So what do we call that process? There's catabolic pathways and anabolic pathways. Okay, so let's talk about those anabolic pathways, right? So anabolic, we're making things, right? We're taking small molecules, we're making big biomolecules. We're only going to do this when the energy charge is high. So if the energy charge is low, we have to metabolize high energy substances to return that energy charge back to our 0.7 to 0.9, right? And replenish those ATPs. So here we are, right? Let's say we have lots of nutrients. We just had lunch, right? So if we just had lunch, what are our ATP levels like? They're very high. So we're going to use that ATP in anabolism in order to make all the things our cells need. But as we do that, what happens to our ATP levels? They start decreasing, right? Okay. Now, we have a situation where we have limited nutrients. We haven't eaten in a long time. So what are we going to do? We're going to undergo catabolism, and we are going to produce ATP. So eventually, you'll have a rise in ATP, and we can rise the energy charge, and now we'll be able to undergo anabolism. So these two things are kind of happening simultaneously, right? So you have both catabolic and anabolic processes that happen all the time. Just because you have eaten a meal does not mean that you're only doing anabolic processes, right? Or vice versa. They're happening simultaneously all the time in all your cells. Yeah. Okay. And that's what the flux is. I guess I should save that for that. But sometimes I just get to talking. Right. Okay. So I just told you that both anabolism and catabolism are happening all the time simultaneously. How do we make sure that the cell is only doing what we want it to do? I say we, but that's, you know. How does the cell know when to do certain things? We have to have signaling mechanisms to let the cell know, yes, this process should be active. No, that process should be shut down, right? So how do we do that? There are two different main ways that we can do that. We can regulate the actual protein. So these two up here are protein modifications. We have one and we have two protein modifications. I can covalently modify my protein. The number one biggest one in all cells is phosphorylation. If a molecule is phosphorylated, it's on. If it's dephosphorylated, it's off. And the reverse can be true too. It depends on which protein you're talking about. Some proteins, if they're phosphorylated, they're off. And when they're dephosphorylated, they're on. We're going to see that it's just like a light switch, on and off, phosphorylated or not. Adenylation, acetylation, there are a bunch of different ones, right? Y'all know about acetylation in DNA? Yes, no? No? Haven't covered that yet? Okay. But there are lots of different ones. Then you can also have other proteins or other regulatory molecules that will bind to your enzyme, right? If you have a binding event that occurs, what's going to happen to your protein? A conformational change. The three-dimensional structure of your protein is going to change if it's phosphorylated or if it's bound to a binding partner. Doesn't matter. You're going to have a conformational change. Absolutely. And we know that structure drives function. So if you change the three-dimensional shape of the protein, is it going to have the same function? No. You're going to turn it off. You're going to turn it on, right? So sometimes binding promotes activity. Sometimes binding reduces activity. Depends on the protein. But both cases are examples where you are changing the three-dimensional shape of the protein in order to turn it off or on. Bioavailability is our third way that we can regulate enzymes in metabolism. But you don't actually change the structure of the protein, right? This is like real estate, location, 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 right? So if you're secluded in a vesicle, you have this enzyme, it's this great enzyme, but it's secluded in a vesicle. Is it going to have access to its substrates? No. No, it's not biologically available to complete its job. You haven't modified it. You've just hidden it away. That's bioavailability. You could also change the rate at which you produce the protein, right? That doesn't change its shape. It just changes how many enzymes are actually available to do the work in the cytoplasm, right? Or you could make it degrade very, very rapidly. So as soon as you make it, very quickly you degrade it. Then it's not sitting around and doing its job over and over and over and over and over again because you've broken it down, right? So you have protein modifications, and then you have other mechanisms that don't actually change the three-dimensional shape of the molecule. So protein modifications change 3D shape and therefore function. That is supposed to be an arrow, and I swear I'm writing on a particular place, but you know. Sylvia, and Sam, I don't know. I think I missed where you asked that question. But we'll actually talk about that later, the lac operon. Okay. Right? That was energy. Take a deep breath. We did energy. We did it. That was a really complex section. So your textbook is like this a lot. The very first section is super big and complex, and then the following sections are smaller and, you know, easier. So a lot of times it takes us more than one day to do the very first section, but I think it's kind of important. Okay, so we talked about water. Remember, y'all took y'all little water quiz at the very beginning of the semester? Yeah. So you think you did well? So what was I looking for? What's so important about water? Why is water such a critical for life processes? Why is that? Its polarity is super important, and polarity is dependent upon a couple of different things, right? So you had to look at the three-dimensional shape of the molecule. So what's the shape of the molecule? It is bent. It is bent. Well, so it has a electron geometry of what? Tetrahedral, but it is bent because of those lone pairs, right? Okay. So because it is bent, right, and it has those lone pairs, what happens to the overall molecule in terms of attractive forces? Right, we have electronegativity differences between the oxygen and the hydrogen, which if it were linear would be one thing, it would be nonpolar, but it's not linear, it's bent. So what happens? We end up with oxygen carrying a partial negative, and we have hydrogens carrying partial positive. So those charges are insanely important because they lead to what? Bonds, but not a bond. Hydrogen bond, right? So hydrogen bonding is a result of the three-dimensional shape of the molecule, and therefore the partial charges, right? And if water did not have hydrogen bonding, we would not be here, period. So we know that hydrogen bonding is not a covalent bond, right? It's much weaker than covalent bonds. So we really call it an electrostatic non-covalent interaction. And that is what drives life. And that's kind of a big science thing, right now. How can we find life that maybe won't be dependent upon water? What would that look like? That's kind of a thing they're doing right now, which I think is super interesting. And so the effect of that is huge in terms of our cellular, how it functions in our cells and what it does for us. And the other thing that we're going to talk about is also how that results in ionization of water, right? So when we talk about ionization, what are we talking about? Acids, bases, right? All that kinds of stuff. So, okay, and we ended. All right, so next time we'll do water, and we'll do like membranes is, I don't know, like 3 slides. It's not much. And y'all already know lots about water. So we'll have a little activity next time, and we're almost done. Y'all have a great rest of your day.
I just want to
Let
make sure.
me ask, anybody have anything on the Zoom? Any questions? See you later. Okay, I'm gonna go ahead and end the Zoom, and Sam, when I get back to my office, I am going to send you an email, so hang tight.